All right, we're going to go ahead and get started here. Hello, everyone, and welcome. Thank you for choosing to spend your valuable time with us. Today's webinar will cover getting started with wolfSSL in 2025, presented by wolfSSL Engineer Manager Chris Conlon. My name is Emma, and I will be moderating the webinar. All attendees will be in listen-only mode. If you have questions, please use the Q&A box. After the presentation, Chris will answer your questions. As always, our webinars are recorded and made available on our YouTube channel. If you'd like to stay updated with the latest from wolfSSL, follow us on Twitter, connect with us on LinkedIn, and subscribe to our YouTube channel. Feel free to contact us via email at facts@wolfSSL.com if you have any further questions. Before we dive into the technical presentation, I'd like to provide a brief overview of wolfSSL. Today, wolfSSL secures over 2.5 billion connections. We have more than 2,500 OEM customers and dozens of resellers. wolfSSL consists of over 50 dedicated employees, primarily engineers. This progress is of course supported by a strong partner network that we are very proud of. Since the beginning, our engineering team has developed several embedded security products, including wolfCrypt with DO178 support, a FIPS 140-3 certification, and a FIPS-ready offering, MQTT up to the V5 specification, SSH v2, TPM 2.0, a secure bootloader known as wolfboot, Java wrappers and JSSC support, and commercial support for curl, and our newest product offering, wolfHSM. These offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. Now, I'd like to turn it over to Chris to discuss getting started with wolfSSL in 2025.
Thanks, Emma. Hi, everyone. My name is Chris Conlon, like Emma mentioned. Today, we're going to talk about wolfSSL, our SSL and TLS library, and how you can get started with that. Everything from downloading it to a little bit about how the package is structured. We'll talk a little bit about what TLS is as a protocol, how you can use wolfSSL pretty much from the most basic level on a client or server. Of course, you can expand that using any number of our APIs or functionality. And then towards the end, I'll give a demo of running our wolfCrypt test and our wolfCrypt benchmark application, which can be two pretty helpful things for when you're evaluating or getting started with wolfSSL. First, a little bit about the SSL and TLS protocol. This has been in development for a while. It started with SSL 2.0 in 1995. Now we're all the way up to TLS 1.3 and DTLS 1.3 as the most current standards. wolfSSL does support both of those. Here's the RFC numbers of some of these protocols for your reference. If you're not familiar with DTLS, that stands for Datagram TLS. That's a version of TLS that's meant to be run over unreliable protocols such as UDP. TLS 1.3, the latest version of the protocol, was in development for quite a while. We had a fun time following it between 2013 and 2018. It went through a lot of different drafts before it was finally finalized in RFC 8446. If you're not familiar with it, the big things that changed included algorithm changes, taking out some of the old insecure features. A lot of the handshake messages are different now, and there's more of them that are encrypted. So everything after the server hello is now encrypted. There's a new 0 round trip time mode where you can send application data in the first flight. The key derivation functions have been redesigned, and there's also some changes to how session resumption are done. The big things for you as a user are it should be faster. So instead of 2 complete round trips to establish the handshake in TLS 1.2 and earlier, TLS 1.3 only requires 1 complete round trip. This especially means it's more friendly if you have a high latency network, just because the required time to establish that connection is going to be shorter. And then you do have that optional 0 RTT mode where you can send data in the first flight. That can be helpful for some use cases, but oftentimes we don't see that used too often yet. The second big advantage is it's more secure. So yeah, the protocol designers removed a lot of the old insecure algorithms and modes, making it more difficult to use these by accident. So, in previous versions of the protocol, some of these things may have been enabled in the library, and some users may not realize they were using them, causing some insecure connections to be happening. It can also be more flexible for some use cases. There's a new key update message, which allows you to rekey the connection without reestablishing the whole session. You can do post-handshake authentication. In previous versions of TLS, you needed to do the certificate verification in the handshake. Now with TLS 1.3, you can do that anytime after as well. And then some of the removal of those old features can help reduce the library footprint size, depending on how you have the library configured. We have a lot of great information on our website. If you want to learn more about that, you can go to wolfSSL.com/TLS13. And this is TLS 1.3, but we do support DTLS 1.3 as well. This is a simplified diagram of the OSI model, just showing you kind of where the SSL protocol sits in relation to your transport and internet layer of TCP/IP. Commonly at the bottom, you've got the SSL subprotocols shown in blue there, and then you have application protocols in green. Something like HTTP can be unsecure, sitting right on top of your transport layer, or you can have HTTPS sitting on top of SSL and TLS. TLS comes in, provides you with authentication, confidentiality, and integrity. When a client and server first make a connection, they go through the handshake process. That's what we were talking about with the round trips on the previous slide. So you can see the first message that's sent over is the client hello. There's then several round trips that exchange certificates, potentially set up shared keying material, finally leaving you with a secure connection down at the bottom where you can exchange messages. TLS uses what's called a cipher suite. This is a string representation of the algorithms used in the connection. This is a format of a TLS 1.2 and before cipher suite string. It started with the protocol, followed by a key exchange algorithm, a bulk encryption algorithm, and a mode, and then lastly followed by the message authentication function. These are some examples. If you've configured SSL before for a project or for a web server, you may have seen things like this. Now with TLS 1.3, the cipher suite representation changed a little bit. It no longer includes the key exchange and signature algorithms in that. So now you have a protocol, bulk encryption, algorithm, and a mode, followed by the message authentication function. And what this does is it shortens up the string, but it also makes the cipher suite list much shorter. So you can see TLS 1.3 only has these 5 cipher suites. Now that we've talked about the protocol a little bit, let's go into the wolfSSL library proper. I mentioned we support up to the most current standards of 1.3, DTLS and TLS 1.3. Footprint size can vary. If you're on an embedded platform with an optimized embedded compiler, you can see footprint sizes, 60 to 100 kilobytes. If you're on a Linux system and you compile in everything, it's going to be bigger than that, of course. Everything is meant to be very modular, so you can compile out features, algorithms to help meet your footprint and your use case requirements. Runtime memory ranges between 1 and 36 kilobytes of RAM per session. The biggest consumers of that are the TLS IO buffers, which are 16K each, as defined by the RFC. Of course, wolfSSL is going to be much smaller than OpenSSL, so it's more friendly for fitting onto your embedded devices and your resource-constrained type devices. We do support 30 to 40 operating systems now and RTOSes. Most of those you can see listed on the bottom of this slide here. That's everything from your Windows, Linux, Mac, down through a number of RTOSes down to just a bare metal environment. wolfSSL has an OpenSSL compatibility layer. This can help you migrate from OpenSSL to wolfSSL. We've integrated into a number of the popular web servers. So if you want to run Apache or Nginx, Lydie, or Mongoose with wolfSSL underneath, you can do that. We like to take advantage of hardware cryptography when we can. This will provide you a performance increase of somewhere around 8 to 10 times typically. And we support a lot of those different platforms now. Usually those are switched on just by defining a specific define associated with that port. wolfCrypt is NSA Suite B compatible. We also have some validated versions of wolfCrypt and wolfSSL available for FIPS 140-3. We have a DO-178C certification for avionics, and then just a lower level ACVP certification around the cryptography algorithms. We think it's fun to port ourselves into open source projects. So we support all kinds of open source projects with wolfSSL underneath. We have a repository on GitHub, github.com/wolfSSL/OSP, where we'll put patches to these projects. Of course, we prefer to upstream our support, but if that's not possible or that's still in progress, we'll put the patch in this repository. But it makes it so you can compile things like Nginx or OpenSSH or libsignal with wolfSSL and wolfCrypt. wolfCrypt sits underneath wolfSSL. This offers all the cryptographic operations and implementations. This slide shows you everything that wolfCrypt currently implements. It's all your standard algorithms that you'd see around with some more progressive ones like Cha-Cha-20, Poly 1305, and also some new post-quantum ones like the MLChem and MLDSA. In regard to post-quantum cryptography, this is something we've been working on for quite a while, even before NIST started their post-quantum competition. Right now, we've been doing it in kind of a piecewise or stepwise approach. Starting on the left, wolfSSL with no post-quantum support. We then moved on to our next stage, which was integrating third-party libraries that implemented the post-quantum algorithms. So you could use wolfSSL with things like liboqs, PQM4. And then the third step, which is what we're in right now, is actually doing our own implementations of the post-quantum algorithms. So we have MLChem, MLDSA, LMS, and XMSS, all implemented inside of wolfCrypt. Those are implementations that we've done ourselves. We've optimized for embedded platforms as best as we can. To download wolfSSL, you can get us from our website or from GitHub. We'll put our stable releases on our website, and then you can follow our development progress on GitHub. I usually like to walk through what's inside of the wolfSSL package. When you download it, it's not, we're getting more and more things inside the package now as we add more support for different platforms and features. So it's not as obvious when you first look at it, what are the important parts. So we'll just walk through some of the highlights here. So this is a version of the latest wolfSSL that I downloaded before our webinar here. The IDE directory is where you'll want to look for project files for your favorite IDE. So if you just want to open up a project file in the IAR eWarm or ARM-Kyle MDK ARM or Xcode, something like that, just open up the project file, hit build, and you end up with a wolfSSL library. That's where you'll want to look. If we go down to the certs directory, this has example certificates and keys. We use these for our own testing. They can also be helpful for prototyping in a kind of an early evaluation phase before you move into your own certificates and keys. There's a number of ones for client servers, CA certs, some different bit length, RSA, ECC type certs, some example CRL lists and Diffie-Hellman parameter files. If we go down a little bit more, you'll get to the configure script. We'll talk about this in a little bit. This is what you'll use to configure wolfSSL on Unix, Linux type environments. The examples directory has some helpful examples, an example client, server, echo client, and echo server. These can be a good API usage example of some of our features. They can also be a kind of a test bed for you to connect your client or server to while in development. And then if you're looking for more examples, we have a separate GitHub repository called wolfSSL-examples linked here. And that'll have a lot more examples of individual specific things. Like if you want to do like an AES encrypt, decrypt, or you want to encrypt a file or do an RSA sign verify, things like that. The gen certbuff Perl script, this is used to generate C arrays from certificate and key files. So we use this to generate the wolfSSL/certs_test.h header. So it takes our example certs and keys and puts them in this header file as C arrays. We also have another script under the scripts directory called dir2c.pl, another Perl script, but this one will take arguments where you can give it the cert input, the array name, and then the output C file to put it in. That can be helpful, or those types of things, if you're on a platform with no file system, or you just don't want to deal with importing and loading files. Next, we'll go all the way down to the wolfCrypt directory. This is the source file directory for our crypto layer sources. It's structured like wolfCrypt source aes.c, for example, has our AES implementation in it. If we go down to the wolfSSL subdirectory, this is our header include directory. wolfSSL headers at the TLS level are just under this directory, wolfSSL. The crypto layer headers are under wolfSSL/wolfCrypt. And then our OpenSSL compatibility layer is under wolfSSL/OpenSSL. Down towards the bottom, you'll find our Visual Studio solution files. If you're on Windows, you can open those up and build the library. The wrapper directory contains our C# wrapper. We do have other language wrappers for things like Java, Go, JavaScript. We package those separately. They're a little bit bigger in size, so we chose not to put them directly into the wolfSSL package itself. Now that you've got wolfSSL downloaded, let's look at how you build the library. If you're on Linux, Unix type system, and you have autoconf, this is the most widely used method. You're going to use configure to configure the library, and then make to build, running sudo make install to install the library artifacts. Configure has a lot of options you can pass to it. If you do --help, you'll see the list of enable options. These can also be turned into disable options. So that first one, --enable -aesgcm, could also be noted in your configure line as --disable -aesgcm. And the help menu there will tell you which features are enabled by default and which are disabled by default. Some also take arguments that can change the behavior of that option. Here's an example of configuring with ECC and DTLS enabled. If you want to pass a preprocessor defined through configure, you can do that using the cflags variable. Here we're defining a define called example_define. You can run make check. That'll compile the library if you haven't compiled it yet. It'll also run our built-in unit tests that we have in wolfSSL, printing out a nice summary for you of what passes and fails. To install the library, you'll run make install or sudo make install. The artifacts will get installed into user local include and user local lib by default on Linux. The artifact name is libwolfSSL.so. If you're on Mac, it's libwolfSSL.dylib. And then the shared library is libwolfSSL.a. If you're a Windows Visual Studio user, we do have the Visual Studio solution files for you. You can open up the wolfSSL 64.solution. That'll contain 32 and 64-bit library and project files for the library proper, and some of our examples, example client server, echo client, echo server, and our test suite and sniffer example. We do have more detailed Visual Studio build instructions on our website if you want more of a step-by-step with screenshots type example. Some of our Windows users are on Cygwin, so we run with Cygwin just fine. You'll need the packages gcc automake, autoconf, libtool, make, and unzip. And then you'll just be able to follow the autoconf instructions that we looked at before. In the root of the wolfSSL directory, you'll find an install file. This is a helpful place to look for how to build wolfSSL for a variety of platforms, or at least find the direction to take to look at a next document. So if you wanted to build wolfSSL with CMake, you could look in here and it would direct you towards the right documentation for that. We have another subset of our users that don't want to use those previous methods, and they just want to take wolfSSL sources and put them directly into their own IDE-based project. You can do that just fine. You just need to pull in the right .c and .h files. So you'll need to pull in the TLS source files under ./source, the TLS header files from wolfSSL, the crypto layer wolfCrypt files from wolfCrypt/source, and then the crypto header files from wolfSSL/wolfCrypt. Ever since the beginning of wolfSSL, one of our main design goals has been portability. Being able to port to platforms and being able to port to new platforms easily. So we've tried to abstract out almost all of the system level, platform level dependencies. So things like IO, logging, memory, entropy source, even things like the standard C library have all been abstracted out to different macros that can be overridden in a port layer. You can, if you want to see some of our existing port layers, you can look in our wolfSSL/wolfCrypt/settings.h file. We typically have one defined per port. So you'll see one in there for FreeRTOS, for example. If you're running the LWIP TCP stack, that you can define wolfSSL_LWIP, and a number of others. A few years back, we introduced a thing we call user settings. So if you build wolfSSL with the wolfSSL_user_settings define set, wolfSSL will include a file called user_settings.h. And so our idea here was that you can put all of your configuration settings for wolfSSL inside of this header file. And then wolfSSL will use that during compilation to enable, disable, configure the library. Then when you migrate from version to version of wolfSSL, all you have to do is maintain this one header file, which makes it pretty easy. You can also easily send this to our support team to help, let us help you optimize your build. We have some example user settings files. There's a good one under the IDE Raleigh Crossworks ARM directory. If you look under the examples/configs directory, we have several in there. There's one that enables all the features in the library. There's a minimal ECC only build. And there's also a user settings template where that one you can go through and it's set up for you just to enable and disable sections of the library. For example, like there's a RSA section, an AES section, along with the right defines to tune the library for those areas. A couple applications that we ship with wolfSSL are the wolfCrypt test and the wolfCrypt benchmark application. The test application, it just tests all of the wolfCrypt algorithms are running properly on your platform. This should be the first place that you start when you're getting wolfSSL and wolfCrypt working. All the algorithms need to be passing correctly on your platform before you move on to like a TLS or a higher level functionality. Otherwise, you can run into some hard to diagnose issues. So this application gets compiled by default when you run make on a Linux Linux Unix standard platform. It'll be called wolfCrypt/test/test wolfCrypt. And when you run it, it'll essentially run algorithm vectors on each algorithm compiled into the library, telling you that that algorithm has passed or failed the algorithm tests. The second application we ship is a benchmark application. This lets you benchmark the wolfCrypt cryptography algorithms on your platform. This can be helpful for comparing different algorithms to each other, comparing different library configurations. You might adjust the math library and want to compare our SP math to our fast math. It can be helpful for comparing hardware crypto versus software crypto, or comparing our library to another implementation. When we run this on different platforms, we put reference numbers up on this benchmarks page. You can see the link here, and we'll try to keep that updated throughout the year as we do new parts. So the benchmark application is also compiled when you run make. Its executable is called benchmark under the wolfCrypt/benchmark directory. When you run it, it'll benchmark each algorithm for at least 1 second, giving you the throughput in megabytes per second. So if we look at the test.c and benchmark.c files, they are set up to have their own main function. They're set up to use certificate and key files. They kind of assume you're running on a desktop-like system. and they benchmark all enabled algorithms in the library. If you're on an embedded target, you'll need to customize that for a couple different reasons. First of all, it can be resource usage. So if you define bench embedded while compiling these, it'll reduce the memory usage of those applications. If you define one of these use SERP buffers defines, either 1024, 2048, or 256, they no longer will try to load a file for keys, and instead they'll use certificate and key buffers. If you have your own embedded target, you probably already have your own driver functionality. So you can define no main driver, and then you can call one of these two functions from your own driver code, either wolfCrypt test or benchmark test. That'll kick off running the test or the benchmark functionality. You can also benchmark or test each algorithm individually. They all have their own individual entry function. So looking at basic library usage, so we're going to go through pretty much the bare bones usage for wolfSSL. The first thing you want to do is make sure wolfSSL and your application are compiled with the same preprocessor defines. So if you compiled wolfSSL with configure, we automatically generate a header file called options.h. And the easy way to make sure these are the same in your application in the library is just to include wolfSSL/options.h in your application. That'll pull in all the same preprocessor defines that were used to compile the wolfSSL library. The main header file we have for SSL and TLS functionality is called wolfSSL/ssl.h. We have two main structures, a wolfSSL and a wolfSSL_CTX. The wolfSSL structure represents a session. The CTX variant represents a context. Essentially, a context is a factory for sessions. So an application would normally have one wolfSSL CTX, and then you would create one wolfSSL session per connection. You want to initialize the library with wolfSSL init. If you want to enable debug logging, and you've defined either debug wolfSSL or use the enable debug configure option, you can turn debugging on by calling wolfSSL debugging on. If you need to turn that off at runtime, you can call wolfSSL debugging off. The next thing you want to do is make a context of wolfSSL CTX. You'll do that using wolfSSL CTX new. That accepts a side method. So here we're making a TLS 1.2 client. We have respective method functions like that for different protocol versions and then different sides between client and server. You'll want to set the peer verification behavior. So do you want to verify the peer you're connecting to? You'll want to load in your trusted root certificates. You can load in CA certificates from a buffer or C array using the wolfSSL CTX load verify buffer. If you have a PEM formatted file, you can do that using wolfSSL CTX load verify locations. So now that you've got your context created, now your application will probably go out and make a socket, connect the socket, and then you'll come around to making a new wolfSSL session for that connection using wolfSSL new. If you're using standard TCP/IP BSD sockets, you'll pass the socket descriptor to wolfSSL using wolfSSL set FD. You can then do the TLS handshake on the client side by calling wolfSSL connect, or on the server side by calling wolfSSL accept. When those functions return SSL success, you're done with that TLS handshake process. You can then write data securely using wolfSSL write, or read data using wolfSSL read. When you're all done with the connection, you can shut it down, calling wolfSSL shutdown. That'll send the TLS close notify alert and optionally wait for the response. And then finally, you'll free your own resources that you've allocated at the session level with wolfSSL free, at the context level with wolfSSL CTX free, and then at the library level with wolfSSL cleanup. For API usage details at the wolfSSL level, we have the wolfSSL API reference. This is regenerated every night based on a documentation repository we have. So it should be very up to date. We talked a little bit about the wolfSSL example client. That can be a decent place to look for an API usage example. It can also be used for testing. So if you want to use wolfCrypt only, just for cryptography operations, you can do that. wolfCrypt is set up to have one structure per algorithm and one header file per algorithm. So here you can see for AES, we have wolfSSL / wolfCrypt / AES.h. And then we have an AES structure. For wolfCrypt API references, please refer to the wolfCrypt API referenced in the wolfSSL manual. Again, that's regenerated every night. If you're in a multi-threaded environment, a few notes on thread safety. So generally, wolfSSL is thread safe by design. So multiple threads can enter the library without conflict. There are two exceptions to this case, which you need to keep in mind. The first one is that around the wolfSSL session object, access to that must be synchronized. So for example, if you have two threads, reading and writing to that at the same time from multiple threads will result in undetermined behavior. So you should put some kind of synchronization around that structure between threads. The second exception is around a wolfSSL CTX. So you need to make sure you completely initialize the context before you start making sessions from it. Since it acts as a factory, every time you make a session, all the settings from the context are inherited into the session. And so if you make a session before the context is set up completely, you'll end up with an incomplete wolfSSL session. So what we normally recommend is you just have a single thread kind of initialize and set up the context before you go off and start your multi-threaded operations. Next, a few tips on debugging the library. Debugging can be very helpful for figuring out why connections aren't working or what's going wrong there. Probably the first place to look is enabling debug logging. So if you configure with -- enable debug or define debug _ wolfSSL, you can then call wolfSSL debugging on from your application. Debug logs will have a lot of helpful information. It'll tell you when you're entering and leaving functions. It'll show you details of the handshake process, the certificate parsing, and really it just gives you more context around a specific error. The example client server can help with debugging. If you're developing a client, you can test against our example server. If you're developing a server, you can connect our example client to it. It'll just give you one kind of known working endpoint to connect your one in development against or to. Wireshark can be a very helpful tool. This lets you see the TLS handshake messages primarily. This can also be helpful to send our support team. If you run into a problem and you can capture a PCAP or a Wireshark trace, we can help you look at that and try to identify the problem. Okay, so next I'm going to do a little quick live demo of building the library and then running the wolfCrypt test and benchmark applications. So here I just have a fresh copy of the latest wolfSSL release. So the first thing we're going to do is run configure. I mentioned you can run -- help, and that'll dump out all of the available enable and disable options for you. Let's run a basic configure with no arguments. That'll go off and detect some things about our system. Here I'm running on a Mac. At the end of configure, it's going to print a little summary out for us of all the features that are enabled for this build. Also some information about our compiler and settings. So there's the little feature summary at the bottom. The top has some information about our compiler and C flags. After this, we can compile the library by running make. Here you could install it with doing sudo make install or make install. I'm not going to do that since we can run the example applications just locally from within this directory. So first we'll run the wolfCrypt test application by running wolfCrypt/test/test wolfCrypt. You can see that all of our algorithms passed in this case. Next, we can run the benchmark application by running wolfCrypt/benchmark/benchmark. Like I mentioned, this will benchmark each algorithm for at least 1 second, giving you the throughput in megabytes per second. On supported platforms, you will see cycles per byte listed as well. The metric changes a little bit when we get to the public key operations. Then it'll be operations per second. But you can see how this would be helpful if you were, say, tuning the library, or if you were enabling or disabling different hardware crypto or assembly optimizations. So there we got down to some of the public key and shared secret operations. You can clean up the library by running make clean. Like we mentioned in the examples directories, where we'll have some of our examples, you run those from the same directory root. Yeah, so hopefully you found that helpful, at least for getting started and kind of a general overview. I'd be happy to open it up and answer any questions that you guys might have about wolfSSL.
Amazing. Thank you so much, Chris. To kick off the questions, where would one find other wrappers for wolfSSL? Does this include a wrapper for using wolfSSL with Rust?
Yeah, so usually each wrapper of ours has its own GitHub repository. For Rust, we have a repository for a wolfCrypt Rust provider. I'm forgetting the exact name of that repository, but if you go to the github.com/wolfSSL and just search for Rust, you should see that pop right up.
Perfect. Are there plans to have wolfSSL CMake based build procedure ready soon? A CMake list text file is available, but it's presented as still under development.
We do support building with CMake, on like a standard platform. Some other platforms like Android use CMake, and we have an Android CMake list under the IDE directory, IDE Android, I believe. For CMake instructions, if my memory serves me right, the install file will give you the CMake build instructions. But if not, just reach out to our support team and we can point you in the right direction there.
Perfect. This next one, I did not understand the difference between context and session. Could you please specify?
Yeah, so the context is, there's usually one context in an application, and that contains some of the higher level settings for all the sessions. And then when you make a session, it inherits all the settings from that context. So for example, if you set, the CA certificate list in the context, every time you make a new session, it'll inherit that same set of trusted CA certificates. So it's mainly just a factory, and then you would have one wolfSSL session per connection. So if you had 100 concurrent connections to different server endpoints from your client side, you would have 100 wolfSSL session structures.
Perfect. This one is an application question. If using public email servers like Gmail or others, some of which support TLS 1.3 and some only support TLS 1.2, is there a common API for trying TLS 1.3 as the primary option before falling back to TLS 1.2?
There is. So when we created our wolfSSL context, we gave it a method function. So if you remember the wolf TLS 1.2 client method, if you want to be able to downgrade, there's an SSL v2.3 client method, and that'll start at the highest TLS 1.3 level before falling back to TLS 1.2.
Awesome. Is it possible to use no dynamic memory with wolfSSL and or wolfCrypt?
Yeah, so we have a static memory build of wolfSSL. It's a dash dash enable static memory. And what that does is has a static memory pool, which we'll use instead of dynamically allocating memory from the heap. And that can be helpful in things like safety critical environments where dynamic memory is not allowed.
Wonderful. What would you say is the best way to add my own hardware crypto acceleration support to wolfSSL?
Yeah, there's a couple ways you can add your own hardware crypto support. Um, the most external facing one of those is we call it crypto callbacks. And so you essentially write a new callback that has a kind of a switch statement in there for different algorithms. And then you can call down into wherever you want to do crypto from that point. So if you have a different crypto library or crypto card or accelerator, that's where you could easily plug that in. The other way is to have us more deeply added inside of wolfSSL itself. So we can typically do that, under consulting services in about a week.
Okay, last question here. Oh, actually, we have two more. How easy is it to replace OpenSSL with wolfSSL?
Yeah, replacing OpenSSL with wolfSSL can be done in a couple ways. It depends on your usage of OpenSSL. So the first method is our OpenSSL compatibility layer. So that's several thousand of the OpenSSL function APIs. We have the same function implemented, the same function signature, but internally we call down to wolfSSL logic. So because you have the same interface, your application code can call the same OpenSSL type function names. And then oftentimes that's just changing linking from OpenSSL to linking against wolfSSL. The second way, which is sometimes more useful if you have a lot of applications using OpenSSL, is using our Wolf Engine or Wolf Provider product. And what that does is plug in right underneath OpenSSL as a crypto provider. So if you're only looking to switch the crypto out for like a FIPS validated crypto, you could use Wolf Engine or Wolf Provider to shim that underneath an existing OpenSSL installation.
Wonderful. Okay, where can I find information about compatibility of wolfSSL with other libraries? We want to know as it is possible that our client application uses wolfSSL, but the server is using another library.
Yeah, that's a good question. We do interop testing with most of the major TLS implementations out there. I'm not sure if we have it, I was struggling to find a document at least from memory that we have. But I can tell you that we interop test against, things like OpenSSL, GNU TLS, Embed TLS, and a few others to make sure that we're implementing the protocol the same and the algorithms interop correctly. If you find an issue, though, let us know, and we definitely want to fix that.
Wonderful. Well, thank you so much, Chris, for hosting an informative webinar. Thank you to everyone for joining. I will email a copy of the webinar recording and PDF slides. You can keep up with our upcoming events, meet our team in person, read our blog posts, and get the latest wolfSSL updates by following us on X, connecting with us on LinkedIn, and subscribing to our YouTube channel. If you have any questions, please reach out to us at facts@wolfSSL.com. Thank you again, and we look forward to seeing you January 23rd for getting started with Wolf SSH in 2025. Thank you all.